other.
Sorry.
There are some fluctuations in the force after the buckling. After it is maximally compressed, it will show some simple harmonic motion or something like that. So these are those oscillations which are shown in a long time. But interesting thing happens in this range of like 10 milliseconds. And if I have to show how it looks like in a picture. So initially, as you saw, when I'm compressing with my fingers, I will always go into this state, right? But when I'm taking it into an over compressed state, it will show higher order buckling, and these will decay and go from like n equal to 4 to n equal to 3, then finally it will go into the fundamental mode. And there are two interesting measurements that I'm making. One is the maximum force, maximum negative force that I see in my system.
Excuse me.
Yeah. Okay.
Can you go back to the previous figure?
This one.
No, not this one.
This one.
This one. Yes. No, no. The previous one.
Yeah.
6, I think. Yes. So in the region where F is negative and the F is gradually decreasing and going to a certain particular in the shaded region that you have shown.
Yes.
Initially, the length is decreasing. Now, after certain time, the red one,
yes,
coming into play, and the length is again increasing. What is
yes.
the reason of that?
Okay. So initially the system is getting compressed, but then it will start buckling. So as soon as it starts buckling, there will be an increase in length at this step. So when it is flat, it can be compressed, but all that compression energy goes into these fluctuations. And as soon as these fluctuations start, my length will suddenly jump and increase. So that is what I'm observing as my length increases.
Okay, that means it is the fluctuations which again helping us to helping the system to increase the length.
Sorry.
It is the fluctuations, initial fluctuations, which increase this length again.
Yes. So as soon as the system is getting destabilized, then these fluctuations will appear and length will increase again.
Okay. Let's say I decrease the force for a larger amount of time. I mean, very large time. In
so
that
this
case,
is not in our control actually, how we decrease the force. The system will get destabilized by itself. And we can maintain this like compressed metastable state for a few milliseconds only, and then by itself the system will destabilize.
Okay.
But it does depend on some parameters actually. For example, if I increase my speed of compression, then the force F max will increase. This negative force, the maximum value will increase if I'm pushing it at higher speeds. And if I increase my cross section, then again it will increase. If I increase the cross section, then it is expected, because then I'm going into the rubber kind of regime where my cross section is high, so compression is more and more favorable. But compression is extremely less favorable in the case of, let's say, these very thin rods. So this can also give me some functionality. I can build dampers out of this kind of system, like people can build. I'm just giving theory. So what is so initially, if you are building a damper, then it will directly go into the buckle state. But if I pre-stress my rods, then whatever projectile, let's say projectile is hitting from the left hand side, then higher order buckling will cause more dissipation of whatever projectile force is coming, and more energy will decay.
So there you have force thought. The force is so where the deep of the force is there. So from that case, your buckling starts. The compression period is over and your buckling starts, right?
You would actually expect that the buckling starts when the force changes direction.
Yeah.
But this is our observation, so we are not sure why this happens. So I actually used an image processing algorithm to measure my length at every step. So I wrote a code where I'm detecting my rod in the image, and we have like accuracy to better than a few millimeters, better than 0.1 millimeters. So with that accuracy, I'm measuring, and this is my data that I'm reporting. Ideally, you would expect that the buckling starts from this point, but we have like even in milli, we have the frame rate of like 15,000 frames per second. So 1 by 115 of a millisecond is our time accuracy. And
so I am asking this because even at that, so I mean that your length is getting changing. Your length is changing the direction from much more left side. I mean that.
yes, this is also can be explained because this is the region in which the fluctuations are growing. So as soon as my external force is compressive, my fluctuations will grow. And as soon as my force is not increasing anymore, then the fluctuations will start to decay. So this is actually the region in which my fluctuations are growing. And there is some dependence of f to the power 3 that people have reported. So that is the rate at which my fluctuation grows. So that corresponds to my increase in length.
And the second one is how do you I mean that can you talk a bit about your measurement technique and that how do you measure this thing and the force or the like
measurement technique. Okay. So this is a simple load cell, but it's basically a Wheatstone bridge. We have 4 resistances arranged in a form of Wheatstone bridge, and as soon as there is slight displacement on one axis, there will be some millivolt change in my resistance that I measure at the ends, and that is accurate enough for me to measure extremely small forces. And I actually amplified it with the. I'm showing an amplifier. This is a data acquisition system. So I'm amplifying that signal as well. So that's why I'm able to measure like small forces, not extremely small. Yeah.
But I can't really read from this system. What are the blue and what are the red?
Okay, so the red is my red is my measured length that I use an image processing algorithm to measure length of system. Blue is my motion of the clamp.
Okay.
So the clamp is still continuing to move and applying this external force, and along that way the system will get destabilized.
Right. So you started to increase.
Yes.
And but then your force also has another point where it changes direction.
Yes.
None of that is reflected on.
So here the force is still decreasing, right? After that, system will act as if some external projectile has hit the system, and it will go up down. So there will be some oscillations. So oscillations start after this point.
Right.
And this is on a millisecond scale. If I see on a larger scale, it will be like this.
Right. So but that is more like is there a correlation between how that brings versus how your length fluctuations are happening? Because your length also has some decaying fluctuations, right?
Yes. So there are some fluctuations here also.
Yeah, but that have any correlation with it?
We did not actually find any correlation between them because this thing actually depends on this clamp also.
Yeah, sure.
The other things will start playing some role in that oscillation.
What is that something?
Yeah, this clamp mass will add on to the frequency of
So it
oscillation.
takes the frequency, but then there was some comment made about something doing this power cube.
Yeah. So when I'm compressing the system, my length, initially the system will get compressed, and then some fluctuations will appear, and for some finite time, these fluctuations will grow.
Yes.
And they can't grow like until infinity, right?
Sure.
And as soon as the system reaches its original length, then the fluctuations will start decaying again. So this is the region in which these fluctuations are still growing, and they grow as the cube of force.
Okay, so that will be traced. That is
Yes. I guess it Okay, you're reminding me. I guess it is cube of the time.
Time, right?
Yeah. It's yeah. Okay. So if I plot, this is my time axis. These are milliseconds. So I see this is another thinner rubber. This is like 0.1 millimeter thin rubber. So here I'm seeing even more oscillations, and I see higher order oscillations. And this is clearly how the mode numbers are decaying from like something like 12. They are going back to 1 over a finite time of 40 milliseconds. So what is happening at the micro scale in the rubber? When rubber is like a soft metal system, all polymers are soft here. I have control over all these parameters: the width, the thickness. Which 2D plot? This one. This is more data that will give you more understanding of how these coalesce. And the very initial part is where these grow, and later on these decay. The mode number decays. So I just thought of putting this also.
What are you plotting exactly?
Okay, so my y-axis is time, and my x-axis is my length of the system. So this strip will look straight here, and these fluctuations that I see here, they will be at this point in time, and this one will be somewhere around here. Okay, yeah. So the z-axis is my fluctuation in height. So this is in millimeters. So this will be like 0.1 millimeters or something. Right. So these are the colors on the z-axis. Yeah. So yeah, that's basically I'm comparing. This is a thinner strip, so I have mode number up to 12. In the previous case, I had mode number something like 4. This is like 0.5 millimeters. The other one is 0.1. But it's also very difficult to measure the length in this system because it is yeah. So maybe in this one, but as I go thinner, this also has a finite cross width, right? So if it twists out of plane, then it will be more difficult to measure the length. I need it to be a projection for accurate measurement. Okay, so what's happening in the microscopic scale in this rubber system? So whether it is a rubber or a polymer, they are basically long chain molecules made of hundreds of, sometimes thousands of individual atoms. And these chains, they will entropically be favored to stay in a coiled up shape rather than a stretched shape. Reason being, if I am stretching the atomic chain, there is only one configuration if it is perfectly straight. But when I coil it up, there are like thousands of configurations possible. So this is more entropically favorable state for any polymer system. And this is not as much favorable. That's why I have to apply external force and take it out of equilibrium. This is the equilibrium state. So why is this interesting? Because these molecules, when I stretch them, they have a relaxation time of a few milliseconds over which these will relax and go back to it if I release my external force. So this relaxation time can also be controlled through external temperature. There is a temperature known as glass transition temperature. Above that temperature, the material will behave like a rubber, but below the temperature, it will behave like a glass. So if I stretch these individual molecules and decrease my temperature, the system will become glass and stay in the long chain state. What happens when I increase my temperature again? Then again the molecular motion and relaxation time will cause it to relax back. So this is sort of like showing a huge response. Let me exemplify what I'm talking about. I'm actually able to build huge sheets which can have contraction factors like 3 times or 4 times. And we are using that to construct some general algorithms for shape transformation. So this is what my sheet looks like. This is the long chain molecules that I've frozen by decreasing my temperature. So I increased my temperature, then stretched the sheet, This is actually a common toy that we can buy from market. It's known as shrinky dink. It's made in China or made in US, not in India so far. But so when you take this sheet and draw something on it, okay. So when you increase the temperature, then these individual molecules which are in straight shape, they will want to coil back. So I can, in fact, selectively heat in a few regions. Let me show with an example. Okay. So if I draw some black pattern on top of this sheet and put some light on top of it, this is very small, but I guess we can understand the fundamental idea. If I apply some light on it, only the black region will absorb the heat. What happens? Only the black region will shrink. And as soon as it shrinks, I will get some bending in my sheet. And it will, if I start from a 1D sheet, 1D shape, I can actually have a 2D or a 3D shape. And this has also other applications in building microchannels. So if I make some etching on top of this sheet, it will become deeper and the material will become thicker. So this is also used in building microchannels. But let's see, let me show you what we did. So this is not reversible, it will be permanent. So this is what people have done. This is basic origami, but we collaborated for this project with Professor Nitin Nitsure from Maths, and he gave an idea that we can actually change the curvature of a sheet, the Gaussian curvature of a sheet, by contracting it on certain regions. So in general, if you have a plain sheet of paper, then whether you bend it or do whatever, you cannot change the Gaussian curvature of this system. Let me define what Gaussian curvature is also. So, okay. It's basically known as the product of two principal curvatures. Let's say I'm on a sphere, then the two principal curvatures are the maximum and the minimum curvature of this surface. So if I am on a sphere, then the product of these two will be my Gaussian curvature, and it will be positive. But if I'm on a saddle like a potato chip or a saddle that you know, then the curvature is called, the Gaussian curvature is fundamentally negative. And there is an interesting feature of this Gaussian curvature that if I move a distance r from a center point, okay, on a flat sheet, if I move a distance r, then my circumference will be 2 pi r. But on a positive curvature, it will be less than 2 pi r. And on a negative curvature, it will be more than 2 pi r. So what is happening is that my perimeter and area is decreasing as I move along a distance r in the case of positive curvature, and it is increasing in the case of negative curvature. So how can I form positive or negative curvature? By using contractions. I can, if I keep the inner portion intact and shrink only the outer region, I will get a positive curvature. And if I shrink only the middle region and keep the outer region intact, I will get a negative curvature. So that's what we did. We actually measured how much region we want to contract. So we built and printed patterns with a simple printer. So this will cause only the black regions to contract, and this is the negative curvature that we get. This is a positive curvature, and this is a symmetric pattern. If we make it non-symmetric, we can even get a shape such as an egg, like we see here. And this pattern is also scale invariant. So this is a negative curvature, and we could reproduce it at all scales. So, but this system is still not algorithmic. We just came up with some ideas and we drew some pattern and it works out. But this is not algorithmic.
Hello?
Yeah.
Yes. How do you create a non-symmetric pattern in Gaussian curvature?
Sorry?
How do you create a non-symmetric curvature in Gaussian curvature?
I simply drew this in Photoshop and printed it on top of this plastic sheet. So this plastic sheet that I showed, you can feed it into a printer and print on top of it. Is that okay?
Yes.
So we also had to do some surface measurements, like what is the expected final length that we expect in the shape case of egg, and we had to contract accordingly. But it can be done numerically. So, okay. But this procedure is not algorithmic. What if we have to go to a general shape with any kind of surface curvature? So let me give two examples. On a curved surface, this is another property that if you have to measure the distance between any 2 points, then on Euclidean geometry, we know that it is dx square plus dy square, right? But in the case of a curved surface, we define the surface in terms of this metric, and this is 1, 1 and 0, 0 in the case of Euclidean metric. But in case of a curved surface, we will have this form of distance between any 2 points. Yeah, question.
So, sheet on which you have printed out this pattern.
Yes.
You are effectively
By exposing it to infrared light, any light can work actually.
that's right. You heat it up with light,
Yes.
and then it bends, expands, contracts.
So it will only contract.
It will only contract. Right.
Yeah.
But then, so if I want some things to contract more, how do I?
I increase the pattern area.
No, but suppose I want a symmetric shape only, but I want one part to just bend more or contract more.
So let's say this is my symmetric shape, right?
So I start with that. I want, say, the upper two things to contract much more than the other.
That's what I'm doing in this egg shape, right? I'm causing it to contact more in this shape and less in upper
So
part.
the only way to make it contract more is to actually draw larger patterns. and
Yes.
select them.
So, yeah, so the-
the entire thing with the same amount of heat, so
Yes.
you can't fine tune.
Yeah, I cannot control the heat per se. It could be done, but I have not chosen to do that.
Sure.
I've chosen to only control the pattern. So this is my central point. If I move a distance r, this is a flat sheet. So my parameter will be 2 pi r, right?
Right.
But I know I can do some numerical calculation on my target shape and see what is the actual circumference
Mhm.
on my target shape.
Okay.
And my contraction factor is, let's say, 0.5. Then I can find out what is how much I have to draw, because if I draw like 50% black at a distance r, then half of it will 50% black means if I have initial length of 1, it will go to 0.75.
Okay.
Right? You get it?
0.5.
No. So I have let's say this circumference is 1.
Yeah.
Then I draw 50% black. So 0.5 is white, 0.5 is black.
So you say that the 50% will shrink half of it.
Yes.
0.25 is
Yes.
1%.
Yeah. So that will shrink half, and I can get some contract. That's my numerical calculation.
But then now, if it's only about contraction factors at a particular radius,
Yes.
this how much part shrinks, it can be spread out in all sorts of different ways. In the sense that for the same target shape, maybe is it possible that you have multiple
Yeah.
starting shapes?
Yeah. There are multiple ways to do that. I could actually split it into. This is like split into 8 parts.
Yeah.
I could split into 6 parts, but or even higher.
Right. So when you are actually looking at a target shape and getting an initial print from which you're getting, the program doesn't care whether it has multiple starting points.
Yes. Yeah, so you actually have to repeat this pattern and optimize, because a smaller lens will absorb less and broader lens will absorb more. So there are those complications also. So you have to do few iterations, and finally you will hit at what's the best way to achieve it. So one interesting feature of this is that when you are transporting this when you have to transport these sheets, if you have to transport 3D objects, it will take a huge amount of volume. But you can always transport flat sheets by stacking them on top of each other. And at the target site, you can actually convert them to 3D. So this is one useful feature functionality that we get. So when we are generating a general metric, we cannot continuously do that. We have to choose a discretization scale. So let's say this is like 10 millimeter scale that I chose. Then I have a circle here. This is the approximation of a circle, and I calculate the eigenvectors based on my radius of curvature, and then again I shrink only in those regions according to the eigenvalues of my metric. And metric will also give me the direction orientation of these contraction vectors. But in this simplified case, there is this orientation directly corresponds to the geodesics on my surface. What's the geodesic? It's the latitudes and longitudes in the case of a sphere, and these straight lines in the case of a negative saddle curvature. Okay. So for Euclidean, I will give an example. For Euclidean geometry, this will be the off-diagonal terms will be 0 and these will be 1. For any orthonormal, for any surface where the vectors are orthonormal, there will we can always change its orientation and diagonalize it so that the off-diagonal terms will be 0. So these geodesics are, so these lines are exactly the points where this is the orientation at which my metric gets diagonalized. So these are my eigenvectors that I get.
So it's saying that the sphere on the top is related to that diagram just below.
Yes.
So which point of
This is the pole of the sphere, you can say.
Okay, so this is the south, north, whichever.
North pole, you can say.
North pole is that.
Yeah.
This
And
is
we
south.
can actually we can't generate a whole of a sphere.
So you can topologically get two patches of the sphere.
Yes.
Right. So say you look at the northern patch, that's fine. So this square will generate which part of the sphere? How much of the sphere?
So you can say like this much portion. Okay. Because I'm limited by my contraction vectors.
Right, sure.
Yeah.
So if I want to make a sphere which is of this much, say radius r,
Yes.
1 centimeter sphere I want.
Yes.
How much of a paper will I need? I can contract to 1 centimeter sphere.
It depends on as we keep on increasing these black regions, there will be they will act like free hinges. They have to interact with each other also. If they act like free hinges, then they can bend in any random direction. So I cannot have extremely huge black regions in my system. So because some extra non-linearities will creep up into the system. So that's why I'm able to demonstrate only small regions of it.
So if I take a 1 centimeter square sheet, what
Yes.
is the curvature I get for the?
So yeah, so this is like this is like a 3 centimeter by 3 centimeter sheet. So if I go into let's say one full half sphere, then then I'll have to my scale of discretization have to be chosen actually, and I guess by repeating it a few times it could be done. Yeah.
Final actually.
So this is one project in which we tried to give a general algorithm for creating any shape from flat sheets. So now let me talk about another project that I did. Here we actually played with the 3D geometry of our system. So if we have cellular soft material which is made of rods connected with air between them, then I can actually compress it in 3D, right? If I start from a square, I can compress it into any shape and removing air from a few regions. Only problem is that it will not stay in my final state, right? And actually, if I compress only at the two axes, I will observe something like this, that there will be a plastic zone formed in the system. So this plastic zone has some interesting property. You have played with sponge in everyday life, and you know if I poke it with a stick or with a finger, then it will come back to its original shape. That's because of the elasticity of the networks formed by these rods. But okay, so what I've done here is that I compressed it on one side for demonstration purpose, What's happening on the microscopic scale is that these rods are buckling and getting connected to each other by friction, by frictional coupling. And if I now poke the system with an indenter, the memory, whatever deformation I've done to the system will stay. So I'm calling this as writing memory on top of a cellular material. And if I have to, it is reprogrammable, because if I have to erase it, I'll have to simply remove the external stresses from the system. And if I compress it again, then this initial shape that I wrote on top of it will not be there anymore.
I don't understand how you say that.
Okay, so this is my experimental setup. I take a piece of foam and then I compress it. When it is in a compressed plastic, I'll call this state as a plastic state. And this is an elastic state, because if I poke it, it will come back. But in the plastic state, if I poke it, it will not come back, because at the microscopic scale, these things are getting coupled and getting stuck. You can say pinning, some kind of pinning is happening. So what will happen, what I'm showing here is, if I compress it in this way, then I can write different kind of shapes on top of this. And now if I remove the external compression from the system, the sponge will come back to original shape, right? And there's no reason for these indentations to stay when I'm compressing it back. So it will be, these will be released. The pinning of the systems will be released. And so that is known as the erasure of this memory. Okay, why is it a memory? So whenever we talk about memory, we talk about a few properties, like whether you can store it for a long time, whether you can read it, write it, and erase it. So all these properties are being shown here. I can write this memory, I can erase it, I can store it also, because as long as I keep it in a compressed state, it will stay.
It's not robust.
Yeah, you are right. This is not robust, but I can use one property to make it robust. One property that I talked previously. I actually should have put a glass transition temperature curve here, but if I convert it, reduce the temperature and convert it into a glass, then it will be a memory that stays for a long time. And you may be wondering, how is it useful in technology, right? But the charge trap flash and the SSDs that we use in our computers, they have they are based on quantum mechanics, and they have a decay time. They store levels of charge, and these levels of charge can decay over a few decades. That's why you may have heard that in Antarctica they store a huge mechanical memory based information storage. There are some data centers in Antarctica where they store memory and information about the human civilization for hundreds of years, so that if some apocalypse or something happens, then you can go back and derive all the information that civilization got. So all those forms of memory are mechanical memory, because we need to store it for an extremely long time. Other examples of mechanical memory could be your usual CD. So a compact disc, or the LP records, those black big discs that you used to see. Those are common mechanical forms of memory, but they are not reprogrammable. And there is no, they are quite optimized. That's a mature technology, but this is something new that we are proposing. And we also have a few parameters that we can play with. For example, how much deep we push our indenter into the system, it will stay for as long. The stored memory will be proportional to how deep we indent our system. Right. So this is also an analog form of memory, because in your usual form of memory you have zeros and ones, right? But actually, even in the charge trap flash, there are levels of charges that you can store. For example, whether it is 10 electrons, 20 electrons, or hundreds of electrons. This is similar to that. This is in analog memory. How much depth to which we store it is also one piece of information, and it's a continuous piece of information. That's why I'm calling it an analog memory.
depends on the depth.
Yeah, yeah. How much depth I indent the system to.
So will that change if you go deeper and deeper?
So there is some limit to how much can be stored. If the edges will start playing a role if I compress it extremely to a huge depth. So this is one project that we are writing. Sorry. Okay. Yeah. So this is my force and this is my depth. So if I so I'm doing repeated measurements and I'm not erasing the previous memory. So this outer layer is my outer curve is my envelope, and I see that if I have some already written memory on top of this system, then I will not go on the initial curve. I will follow this curve. Let's say this blue curve. I'll have to blow it up actually, but if you follow this blue curve, then it is not following the envelope until it reaches the previously stored memory. X-axis is my indentation. Indentation is my depth of compression of this thing. So let me actually blow it up if I can. So on x-axis I have indentation. So you can see that okay, I will blow this also. How much time do I have now? So if I keep erasing my previously stored memory, I will follow this outer envelope. But if I don't erase it, then whatever memory was written, an effect of it will be that my new stress that I measure will be lower. And it should be ideally zero, but there are some contacts that will happen with the boundaries of the system. That's why it is a finite value. And as soon as it reaches the previously stored memory, let's say in this cycle I stored memory up to black. So that's why it is not following the envelope until this black point, but after that it will be a linear curve, which is my control parameter is indentation. That is not my control parameter. My control parameter is the displacement, but my measurement is the force. So I'm externally, this is a soft system, so I can push it as any much as I want. But the response of the system is what I'm measuring. So, okay.
Maybe we can finish it off and then take more questions.
Yeah, okay. 5 minutes only now. This is my last project that I'm showing. So this is in collaboration with Professor Trideep Sadhu from DTP. And what we are forming is an optical tweezer. What's an optical tweezer? Let's say we have a spring force and a mass is linked to it. I'll skip it and show you directly how it happens in case of a laser. So I'm focusing my laser to a very small region, and it will provide some external force to a micrometer sized polymer particle, because the polymer particle is a dielectric material. And it happens that due to electromagnetics, but it can be understood from basic physics also that it will want to go into the maximum electric field because it will get polarized, and we know that if there is polarization on top of it, then the total energy of the system is minimum when the system is in maximum electric field, if you can understand. So what happens effectively is that we get a force towards the maximum intensity, and it acts like a spring force. So the force is linear, similar to a spring force. And I prepared a sample in water and put these micrometer sized particles in it, and then I'm shining a laser on top of it through an objective. So this is an objective lens of a microscope which will focus my laser. I'm also using some more equipment such as this. The laser shoots out a thin beam, but I'm expanding it because as soon as I put it on this special device known as a spatial light modulator, I can change the shape of my laser. So this is how a laser looks like a dot. but I can actually play with the liquid crystals on top of this special light modulator to give it any shape. So this is one pattern that we gave, and another pattern I will show later on, which is very useful. And the particle, we are using image processing again to detect the particle. We actually did subpixel detection of that particle. So usually you would expect that if I have an image of, let's say, 100 by 100 size, then the particle measurement would be limited to what pixel it is on the x-axis and on the right axis, let's say 50 cross 50. But we can actually detect a Gaussian shape on top of this particle. From the intensity pattern, we will get a Gaussian kind of shape, and if we fit a Gaussian on top of it, then we will get a subpixel accuracy of where my particle is. So that will give me accurate measurement of where the particle is, and I can write this is a Brownian system inside water. I'm putting a micrometer sized polymer, lightweight polymer particle. So this is a Brownian system, and this is my differential equation I can write. This is force. It will be proportional to my potential, and whatever damping forces are there due to my fluid, due to the difference between velocity of the fluid and the particle. And finally, there will be some random kicks to the particle, which also is the reason behind your Brownian force. So this is how we can write the differential equation for motion of particle inside this microscopic system. This is known as a Langevin equation. And since these are very light-sized particles, the other three terms will be dominant and the inertial term will not be as dominant. So we can actually ignore this one, and we end up with a first-order differential equation. We can do simulations of this system also. But what I actually did with this one is we generated a circular shape which also has a force along the circle. So this gives us a non-equilibrium system. Ideally, if I generate a circle or a potential like this, then it will be equilibrium. In the absence of any external force, if I'm only having some external random kicks, then I know the Boltzmann formula that my potential is proportional to e to the minus u by kt, right? That is what gives me the measurement of the potential. But that kind of a measurement is not possible in a non-equilibrium case. So this is how this is an ideal potential, cosine shaped potential in the absence of external force. But if I have external force also, then I can actually add an f theta term to my potential, and it will look like a tilted potential. And this is on top of this circle actually. So I generated this circular trap. If I put a particle, it will want to stay on this circle only. It will be constrained. And if I don't have external force and I let the particle stay on the circle for a long time, then from the probability of particle positions, I can calculate back my potential. Right? Yeah, you have a question.
The reason we make the circle is just so that you get the track.
Yes. Yes.
Why can't we just use a Lagrange question?
Sorry?
Why can't we just use a Lagrange question?
This is what it is. This is a Lagrange Gaussian beam.
We're maybe a Lagrange question.
Yeah. So Lagrange Gaussian beam is actually something like a stair. If we take a single circle, then the particle will not have any force along the circle. But Lagrange Gaussian beam is like a staircase of spiral stairs, and there is constant force on top of the particle because it can. Okay, how can I simply explain? But okay, so if we create a circular trap, there is no force along the circle. But if I also have a force along the, if I want a force along the circle, then I will have to have two components of, I will have to use two lasers ideally, right? One laser will create this circle and one laser will keep on pushing this particle along this circle, which will apply some force. But Lagrange Gaussian beam is a special kind of beam which already has these two features built in. Okay. So I get a tilted potential. If I don't use the external force, then I have to leave the particle for a long time. And what happens often in these experiments is the particle will not be able to probe the entire track. Particle will want to stay in one position, and it will take a huge, logarithmically huge amount of time for the particle to move around the whole of the track. But if I put an external force, what happens is the particle is able to cover the whole track, but this is no longer an equilibrium system where I can use my Boltzmann equation to find the potential. So we did some, okay, so we can actually cancel out some terms, and okay, so the inertial term is already cancelled, and P is my periodicity of the potential, and F is my constant force. This is my drag force, and this is my Brownian noise. Turns out that I can also make measurements for a long time and cancel my Brownian noise also. So I end up with only these three terms. And since I'm on a circular track and not an open path, the potential at the beginning and the end will be the same. So this term can be cancelled out if I'm going from 0 to P, which is my periodicity, and if I can directly calculate my force. And what is my observation? My observation is x dot, which is the speed of the particle along this track. So I simply have to make measurements of the speed of the particle along this track. I do have videos, maybe I can show on YouTube after some time. But okay, so I measure my velocity of the particle along the track, and I will get the force as well as the potential. So this is possible only on a closed path. So that's why geometry is giving us some useful functionality in this system. So I will thank you with this slide, and we can move to questions now.
I have two questions. So, these patterns are the different beams. These are the looks like the interference patterns. So if it produced by these liquid crystal planes, how these are produced.
Okay, so in Fourier optics, we know that a lens acts as a Fourier transform. If we have a wave front which is flat, Fourier transform of it turns out to be a single point. And if I want this particular kind of shape, then I need to do an inverse Fourier transform of it and see what waveform I get. Once I get that waveform, I need to generate that waveform on top of my flat input of a laser, right? How do I do that? I use these liquid crystals, and I can actually tune the paths that light will take. So if these are like a straight shape, then light is going very little through this optical through this material, and if these are like perfectly aligned, then my path through the light will increase, and effectively I create a grid of 500 by 500 pixels. This is what that device, special light modulator, does, and it will tune my flat wavefront into whatever shape I want. Wavefront is something that has a constant phase, right? So I can tune my phase through this kind of a device.
And I couldn't understand the philosophy of the optical tweezer.
Why do I have optical tweezer? Okay. So optical tweezer is, forget about optical tweezer. I'm basically using an objective lens. This lens is my Fourier transforming lens. So whatever I give it at the back, the Fourier transform will come here. If I give the Lagrange-Gaussian pattern, I will get a Lagrange-Gaussian beam pattern here, which is a circular. Sorry?
Fourier transform Lagrange-Gaussian.
So this is the fundamental component of optical tweezer, you can say, which is holding the light. And if I had a single beam, it will act like a trap holding particle at one point with some Brownian fluctuation on top of it. But I can create tracks of squares or straight lines or circular paths. Yeah. Okay, motivation was basically to study verify some properties of non-equilibrium physics. So when we have this particle moving on this track, it will have some forward current and there will be some backward current. And there are some theorems in non-equilibrium physics that relate the forward current and the backward current. So we wanted to verify. So the logarithm of the forward and the backward current is linear in current. So that has been proposed and we wanted to verify that. But then this other problem also I hit upon that. Okay, let me think.
Out of P of J, out of the
Probability of forward current.
Yeah, that's fine. So you need to get a steady state and not steady state of this particle. And within that, you're trying to show that the log of the probability. And that is geometry.
Sorry?
Well, for example, if I have thermal, then the probability would be, as you said, it's e to the power minus beta n.
Hmm.
And you say that the energy is not related to the current. The energy is not the current. So you can also the exclusion is symmetric. Take the log at zero. Why? Say take the exclusion of energy.
Any more questions?
Like energy. It's like energy. Log of E to the energy. Yeah, so it's symmetric with respect to the order. So you're looking at log of the average. That is.
Yeah. Probability is already average, right? Probability is like
log of P by itself is not B. So here for P, here there is a entropic production. You want to look at entropy. Okay.
yeah. So there are some.
Derivation measure entropy. Look.
And I also hit upon this problem that the potentials are undefined in this system.
Potentials are undefined after the constant.
Yeah, you will have to like exact values are not known.
That's fine.
Yeah, okay. Fine. Then if there are no more questions.
Any more questions on Zoom? Guys, you can. So there's no one. Everyone's left for last. Good.
Okay.
Fine.
Fine. Then
Okay,
we
then
can stop here.
we can end the meeting. Thanks all for joining. Everyone is left anyway.